The leaders and dear experts, good afternoon. I'm from Suzhou and Jiangsu Syncray company. I'm the founder, Yang Dawei. And next, I want to talk about what we have done in membrane and VRFB, industrialized progress, and so on. Well, actually, the working principle of VRFB has been mentioned by many experts. I want to elaborate. I will just focus on membrane. Membrane is the core of VRFB, and it can pass on the proton, and also it could separate cathode and anode, and use a 2.11 membrane, and the price was very high. It's up to 11,000 yuan. And now the massively used price is 1,000 or so. And therefore, we have done a lot of contribution to this, bringing down the price. Now, there are membrane. Proton membrane is the core. And for the proton membrane, actually, it has two aspects. One is the porous ion transmission membrane. It just uses a molecular sieve. And just now, Professor Wang Baoguo is an expert, and he does the membrane, especially porous membrane for the sieving or siever. And Mr. Li is also working on the porous membrane, and also others have different membranes. So why we have this full coverage membrane? The reason is that the bond valency and so on, and such as the PVDF and also different membranes. So you could see we have the carbon fluorine bond is shorter in terms of the bond length, and also energy is bigger, so it's more stable. And this is why between these two membranes, long fluorine and fluorine membrane, we use the fluorine membrane. And for the exchange, the proton, you could see it's all fluorine and partly fluorine and non-fluorine. Therefore, in the market, this commonly used, which is the full fluorine. So that is the benzene sulfonic acid. But still, porous membrane has some commercial application as well. For the application of fluorine sulfonic acid protein membranes, let me talk about the application of such protein membrane, the performance enhancement, and the cost reduction. And now we have a 5 series. This is uniform. We use the 212 sulfonic acid membrane, and EPTFA, which is a compound enhancement membrane, just for fuel cells, and now it is 8 micrometers. And some of the aspects cannot fit the use of flow battery. And the next one, PTFE membrane, such as hydrogen making, and also some traditional usage, and also the different recovery, and copper or some other electrolyte industry.
As for the manufacturing process for membranes, I mean, we have been in this field for many years. We have tried a lot of technologies, as you can see from this page. We have tried twin screw melt extrusion technology, solution casting technology, coating technology for composite films, membranes. The twin screw melt extrusion technology could be very fast, very efficient, and it has a lighter load on the environment, and it could be better than the solution technology environmentally. However, if you want to go beyond 80 micrometers for the membrane, maybe you want to use the extrusion technology. At high temperature, there could be a lot of byproduct acid generated, and there could be very tough requirements for the materials. And there could be some kind of alloys needed for the processing, and the whole equipment could be very expensive, maybe 20 million USD. So that under that situation, this technology, twin screw melt extrusion technology, is not used much. Also, we could see this kind of technology has a lot of impact on the equipment. And with 212, that is based on another technology. There is no disparity in extension and other kinds of issues. But in this kind of technology, in solution casting technology, things could be tricky. And we have built-in production lines that can produce 150 solid square meters. And there, this kind of large area of the membranes could be very tricky. And with this technology, we can achieve some good features. One thing it is isotropic. On the other hand, it can involve some additives. We can go very thin with this technology. We can go down to 15 micrometers, and we can also go up to 200 micrometers. As you can see, in terms of thickness, it is very flexible. But for different thickness levels, we gotta use different drying processes. And later, actually before solution casting technology, we had another solution technology. Later, we upgraded that to the solution casting technology. With the last solution, we can do some casting on the glass matrix, and then the solvent evaporates, and then we can see the remaining materials to make the membrane. And the consistency and uniformity of the membranes could be very poor in this technology. And then I want to talk about the coating technology for composite membranes. For composite membranes, we can use the coating technology. But in our practice, we use the casting technology of double cellular radiation steel strip. And in terms of the temperatures, you can go up to 200 degrees in the processing. The higher temperature it is, the better bonding we can achieve for the membrane. So that translates into better stability. We are also developing the so-called deep vertical furnace technology that can combine the benefits of casting and coating. We can ensure that all the small holes in the membrane can get the acid, and the acid can be distributed evenly. Now, let me talk about the structure of the membrane. As you can see here, that is the molecular structure of this acid. The quality is very good. We could see the core structure. It is hydrophilic. The branch is hydrophilic instead of being hydrophobic. That is a very good thing for absorbing the acid into the membrane. However, there can be some issue with the molecular bonding that can translate into poor strength and lower stability. Now let me talk about our company. Our company has been around for like 15 years. In the beginning, we used solution to make membranes, and we used coating. We started to develop testing technology for double cellular radiation steel strips and deep vertical furnace technology. Over all these years, we have been iterating success technology. we have two bases. One is in Suzhou, and one is in Taiwan. The Suzhou base has been operating for quite a few years. In Taiwan, our fan base was already put into use back in 2022, and in that base, we have one product line for QRFBs. Currently, we are developing the second phase of the fan base. We expect to launch production for the second phase in 2025, but it depends on our progress made. On 1 square meter of our membrane, we can go up to 1.2 to 1.5 kilowatt of batteries. So if you consider the full capacity, we can go up to 6 gigawatts in terms of capacity. I mean, we can use our membranes to support this much in capacity. Our company is a national level high-tech firm. We're also one of the high-tech star firms in Suzhou, in Shanghai. And we also obtained a project in Shantou. In the field of FBs, we are the only company capable of supplying membranes in large quantities and stable. We have contributed our bits to the industry. In Dawei, we have a 100 MW project, and also many other projects have used our membranes. Our membranes have been tested by the market for years. And we do not only do energy storage, we do not only do VRFBs, we also have a presence in hydrogen energy. The preparation of hydrogen. Next, let me talk about some basic specifications of our membranes. Actually, we can do a comparison between our membrane and the imported products. If you look at the conductivity, our product outperforms this one. In terms of piercing strength, we also have a very good performance. Now, let me talk about the next generation of membrane. Our new generation membrane needs to be developed further. I mean, this kind of membrane has been developing for a few decades. It's first developed back in the 1980s, but now we have not discovered a better solution, a better membrane. So our research is based on this kind of membrane. We hope we can enhance the stability, and on the molecular branch, we have also discovered some room for improvements. With the Sui company, we have their high-performance products in terms of both durability and performance. For short chain, for short molecular chain, there are some issues. Conductivity may be good, but ion transfer, for example, with short chains, with short molecular chains. For long molecular chains, there could be issues at high temperatures. Also, stability could be one of the issues. And we need to conduct both non-molecular chains and short molecular chains. We also consider some solid branches, solid molecular branches. On each of the branches, there could be different ions of the acid. If we can do multiple branches, then we can have multiple acid ions or test the branches. And In that case, we are actually trying to increase the number of cell branches that can enhance the capability of transferring ions, and all in all, that can increase or improve conductivity. In this case, we have our new generation of products, and we want to ensure that we can introduce more materials. We need to introduce more monomers. That when more new monomers introduced, we can have more potential to make more breakthroughs. And actually, when a new monomer comes out, its aggregation could be very difficult. We want to use controlled polymerization, and that can also be tricky. Without the bonding of monomer to the backbone structure, there could be quite some headaches going forward. We'll also consider how we can better achieve uniformity in aggregation. In our lab, we have done some small trials. Yeah, maybe for some trials, we achieve results, but for other trials, things were not okay. We want to ensure we can achieve a good performance slowly. And here, we can look at our testing results. The density, the current density could be 250. And after a large number of recycles, the degradation of the battery is less than 1%. So the degradation of the membrane is also very low, less than 1%. Going forward, I'm sure the future of VRFBs is quite clear. For one thing, we gotta ensure energy density. For another thing, we gotta ensure VRFBs can work properly at higher temperatures. Today, we have many experts from vanadium companies. Actually, if the price of vanadium goes beyond 120,000 per metric ton, things could really go south. Many companies will simply give up because that price is too high. We want to ensure that our products can bring some cost benefits to the whole VRFB so that VRFB projects are more feasible. And we care about durability and stability, as I mentioned. Also, we got to ensure on all the cell branches, we can have better molecular structures. And that depends on a smarter choice of raw materials.
So only with the scaled up, we can reduce the cost for the raw materials, because if we produce 5 tons of membrane and 500 tons of membrane, actually the process is the same, energy consumption and other dilution is the same. And if we have 100 volts increase, we can have a very quick reduction of cost, and therefore we don't want to use a very high profit to sustain ourselves and to grow ourselves, but we want to scale up, and then we can win with quantity. Therefore, our principle is that once we have this bench, the production, our profitability won't exceed 15%. We hope that other material provider in our industry could join us and then reduce the cost and then promote the vanadium battery. Thank you. Okay, thank you. Thank you. Thank you, yeah, Mr. Yang. And now we come to the Q&A session. Any question on site? And for the VRFB, the lifetime, and also it's the advantage, and also it is a highlight, such as the proton exchange membrane. How can you imitate the life under use? How can you guarantee the life under usage condition? Yes, yes. And for every membrane, and then we have our testing data of a single battery, and we've been doing this industry for a long time. Why we always have this fluorine membrane, it is based on the mechanism of life, and actually it won't degrade in 100 years. Therefore, stability is very good, and also we have a lot of cases of our customers, and in Dawei company, the battery 10 years ago, but now they're still up and running and discharging and charging. And also in recent years, after operation, the sulfonic acid is very stable and a long life, and no problem about that. But you know that with the dripping, the stone can be punctured, and if it's operating in flow state, so maybe the membrane will be shocked or will be attenuated, or it will reduce the life. Oh, that's why I didn't push forward the ultra thin membrane. This is very difficult to, and it will be validated by long time. But 50 micrometer is okay because the 50 micrometer thin membrane has been proven in 10 years already.